Imagine the moment before time had a name. No galaxies, no stars, just an infinite black silence stretching across a fabric that hadn't even unraveled yet. What if we could see past the first flickers of starlight, past the birth of matter itself, and witness the origin of everything? This isn't just science fiction. It's the frontier. NASA's newest space telescope is now crossing in real time. The James Webb Space Telescope, spoken as JWST, is more than just a scientific instrument. It's a time machine, designed to peer back nearly 14 billion years. JWST is allowing us to glimpse the universe as it was mere hundreds of millions of years after the Big Bang. That's not just early, it's ancient. In cosmic terms, we're talking about the universe in diapers. At that time, the very first stars and galaxies were just forming from collapsing clouds of hydrogen and helium, the primordial ingredients left over from the Big Bang. And here's where things get mind-bending. Because light takes time to travel, the farther we look, the older the light we're seeing. So when JWST looks across the vast chasm of space, it's not just observing distance, it's observing time. Light from the earliest galaxies has taken nearly 14 billion years to reach us, stretching along the way, due to the expansion of the universe, sliding out of visible light and into the infrared spectrum. This is where JWST shines, literally. Equipped with an array of incredibly sensitive infrared instruments, the telescope can capture that ancient, stretched-out light and reconstruct what the early universe looked like. We're talking about galaxies so faint and distant they'd be invisible to the Hubble Space Telescope, spoken as HST, or any other previous observatory. Galaxies like JD's GSZ 13-0, one of the most distant ever confirmed, which JWST found just a few months into its mission. It existed only 320 million years after the Big Bang. That's like reading the first sentence of the universe's autobiography. But JWST doesn't just reveal the earliest galaxies, it tells us how they came to be. Before this telescope, we could see only the blurry outlines of ancient galactic formations. Now we can resolve individual stars, track the growth of black holes, and analyze the chemical compositions of those early cosmic structures. Every image JWST sends back is a revelation, a snapshot of a chapter we never knew we were missing, and it's not just looking outward in space, it's also looking inward, toward the origins of life itself. JWST's infrared eyes can detect the spectral fingerprints of molecules like water vapor, carbon dioxide, methane, and even complex organics in the atmospheres of exoplanets orbiting distant suns. For the first time in history, we're not just discovering planets, we're analyzing their skies. Imagine a world 400 light-years away where clouds of vapor drift over alien oceans, and JWST can tell us the chemical makeup of that atmosphere without ever leaving Earth's orbit. That's not imagination anymore. That's happening right now. It's not magic. It's engineering. JWST is a feat of cosmic origami. Its 18 gold-plated beryllium mirror segments fold tightly to fit inside a rocket, then unfold with exquisite precision in space to form a mirror 21 feet wide, over 2.5 times the size of HST's. And it operates at a staggering 45 kelvins, just shy of absolute zero, so its own heat doesn't interfere with the faint glow of ancient stars. To block the heat from the sun, Earth and Moon, JWST unfurled a sunshield the size of a tennis court, made of 5 paper-thin layers of kapton, each engineered to reflect and redirect solar energy away from the instruments. If just one piece of this intricate ballet failed, the entire mission would have been compromised. But it didn't fail. Against incredible odds, the deployment worked flawlessly, and what it's already found, within months of becoming operational, has scientists rewriting textbooks. We're seeing galaxies that appear too massive, too evolved, too soon. We're detecting carbon compounds on alien worlds. We're watching starlight that began its journey before the Earth even formed. In essence, we're opening a window not just into space, but into time itself. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. But this is only the first step. In Section 2, we'll dive deep into the incredible technology that makes all of this possible. From segmented mirrors that align to within nanometers, to cryogenic cooling systems that keep JWST colder than Pluto, we'll explore how this orbiting marvel is changing astronomy forever, and what that tells us about the birth of space and time. 2 million kilometers from Earth, in a silent, sunlit void far beyond the reach of repair crews or second chances, floats the most advanced piece of technology humanity has ever built to explore the cosmos. The James Webb Space Telescope, spoken as JWST, isn't just a telescope. It's a symphony of engineering brilliance, operating in a place where precision is the only thing standing between discovery and darkness. But how does this technological marvel actually work? How do you build a telescope that can see further back in time than any instrument before it? Let's start with its most iconic feature, the mirror, or rather mirrors. JWST's primary mirror is made of 18 hexagonal segments, each meticulously coated with a thin layer of gold, chosen not for its beauty, but because gold reflects infrared light better than any other metal. Together, they form a giant 21-foot-wide honeycomb that had to fold tightly into the Ariane 5 rocket before unfolding with absolute perfection once in space. Each segment is made from beryllium, a lightweight metal that doesn't warp in the extreme cold of space. But just having a big mirror isn't enough. These segments must function as one perfectly curved surface, aligned within nanometers. That's 1/10,000th the width of a human hair. To achieve this, JWST uses tiny motors called actuators to adjust each segment's tilt and curvature while it's floating in space. But mirrors don't see, instruments do. And JWST has 4 of them, each with a specialized mission. First, there's NIRCam, the near-infrared camera. Think of it as the telescope's primary eye, scanning for the first light of the earliest galaxies. Then there's NIRSpec, the near-infrared spectrograph, capable of analyzing the light from up to 100 different objects at once, telling us exactly what those galaxies are made of. Next is MIRI, the mid-infrared instrument, which lets us see cooler objects like dust clouds and protoplanetary disks. Finally, there's FGS NIRIS, a Canadian-built fine guidance sensor that keeps JWST steady enough to lock onto its targets with millisecond precision, and an instrument to study exoplanet atmospheres. These tools work in harmony, capturing everything from newborn stars to the chemical trails of alien worlds. And then there's the sunshield. Imagine trying to detect the faint glow of a candle next to a spotlight. That's what it's like trying to see early universe infrared light while basking in the heat of the sun. JWST's solution? A multi-layered sunshield as big as a tennis court, made of 5 ultra-thin layers of kapton, each thinner than a human hair. These layers reduce incoming solar radiation from over 200 degrees Celsius to less than -200 degrees Celsius, a drop of over 400 degrees across just a few feet. The sunshield took almost a month to deploy, with over 300 points of potential failure. And it worked. Every pulley, every latch, every tension line did exactly what it was designed to do. Because it had to. But what's equally fascinating is where JWST is. It orbits a point in space called Lagrange Point 2, L2 for short. Located about 1.5 million kilometers from Earth, this spot allows the telescope to stay in constant alignment with the Earth and Sun, keeping its sunshield perpetually between itself and the heat sources. It's a cosmic sweet spot. Stable, cold and perfect for observing the universe in silence. Unlike the ISS, which orbits a few hundred kilometers above us and can be visited by astronauts, JWST is alone. If something breaks, there's no fixing it. That's why its design had to be near perfect. The road to perfection wasn't easy. The mission was decades in the making. Its budget ballooned to nearly $10 billion. Launch dates were pushed back again and again. And when the rocket finally ignited on December 25, 2021, the world held its breath. If anything went wrong, during launch, during deployment, or during alignment, it would have meant the loss of years, careers, and countless dreams. but JWST delivered. In the months following its full deployment, it began capturing images that were, quite literally, from another time. The first deep field showed thousands of galaxies in a patch of sky no bigger than a grain of sand, held at arm's length. Each galaxy contains billions of stars, and some of those stars might host planets, and some of those planets might have oceans, or atmospheres, or life. JWST isn't just giving us high-resolution images, it's giving us stories. The tales of galaxies colliding, stars being born, black holes feasting, and planets forming. It's telling us how the cosmos grew from simplicity to complexity, from hydrogen atoms to habitable worlds. And it's not doing this with brute force, it's doing it with elegance. Unlike the HST, which captured the universe in visible light, JWST specializes in the infrared, letting us see what was once hidden behind clouds of gas and dust. It can reveal the cold glow of baby stars inside thick nebulae, spot the thermal traces of far-off planets, and map the atmospheres of worlds hundreds of light years away. So why infrared? Because the universe is expanding. The further light travels, the more its wavelength stretches, turning visible light into infrared. Only a cold, dark, perfectly tuned eye like JWST can see it. It's as if we've been watching a silent film in black and white, and suddenly, everything's in color and surround sound. What if everything we thought we knew about the early universe is wrong? That's the question whispering through the corridors of observatories and echoing across science journals ever since JWST began transmitting its first images. Because while this telescope was designed to confirm our understanding of cosmic history, it's doing something far more exciting. It's challenging it. Let's start with the galaxies. One of the earliest surprises came from an image known as the Cosmic Cliffs, a jagged wall of gas and dust in the Carina Nebula, where stars are actively forming. The detail was breathtaking, but the real shock came when JWST peered deeper into space, and further into time. In a tiny patch of sky, the telescope uncovered a population of ancient galaxies that were brighter, more massive, and more mature than expected. Some appeared to have formed just 200 million years after the Big Bang, but were already well developed with complex structures. That shouldn't be possible. According to our best models of cosmology, the first stars, known as population 3 stars, were supposed to be massive, short-lived, and composed almost entirely of hydrogen and helium. Galaxies were expected to start small and chaotic, slowly, merging into larger ones over billions of years. But what JWST is showing us are ordered galaxies, spirals even, existing less than 500 million years after time began. The light from these galaxies is extremely redshifted, meaning it has stretched significantly during its long journey to Earth. By measuring that redshift, astronomers can estimate how far back in time we're looking. And some of the redshifts JWST has recorded are rewriting textbooks. Take, for example, Galaxy JD's GSZ 13-0, confirmed to exist only 320 million years after the Big Bang. It's not just there, it's surprisingly bright. The implication? Either galaxies were forming much earlier than we thought, or they were forming much faster and more efficiently. Now, fast-forming galaxies are only the beginning. JWST is also pulling back the curtain on another mystery: black holes. We've known for a while that supermassive black holes sit at the centers of most galaxies, including our own Milky Way. What we didn't expect was to find them already fully formed in the early universe. In several ancient galaxies, JWST has detected signs of intense activity, light being bent and accelerated in ways that can only be explained by powerful gravitational forces. In other words, black holes were already feeding and growing. At cosmic dawn, this raises uncomfortable questions. Did these black holes form from the collapse of the very first stars? Or could there be another mechanism, one we haven't discovered yet, that creates them even earlier, possibly before galaxies themselves? These revelations are not just fascinating, they're troubling, because they hint at the possibility that our current models of cosmic evolution, shaped over decades of observation and theory, might be incomplete. It's as if we've been assembling a puzzle for generations, only to discover that some of the corner pieces are missing, or were never part of the picture in the first place. Then there's the mystery of dark matter and dark energy, two invisible forces that dominate the universe but can't be directly observed. While JWST isn't designed to detect dark matter itself, it can map how galaxies move, interact, and cluster in the early universe. This movement, especially the rate at which galaxies form and merge, could give us clues about the invisible scaffolding holding everything together. And, while we're questioning the past, JWST is also helping us glimpse possible futures. By observing the atmospheres of exoplanets using a technique called transmission spectroscopy, the telescope is detecting signs of water vapor, carbon dioxide, and methane. It's not just proving that other planets have complex atmospheres, it's opening the door to habitability studies on a scale we've never seen before. Take the TRAPPIST system, a group of 7 Earth-sized planets orbiting a small, cool star just 40 light-years away. JWST has already begun analyzing these planets' atmospheres. If it detects molecules associated with biological processes, like oxygen, ozone, or methane in just the right proportions, we might be staring at the first real signs of alien life. But even without biological markers, the data itself is groundbreaking. Some exoplanets are turning out to be mini-Neptunes, with cloudy skies and thick atmospheres. Others might be dry, rocky, and hot, inhospitable, but still full of clues about how planets form and evolve. And every time we get a clearer spectrum, every time we decode the faintest hint of a molecule orbiting a distant sun, we're answering questions we never even thought to ask. The excitement isn't just scientific, it's philosophical. If galaxies formed faster than we thought, if black holes came first instead of last, if the elements of life are common across the galaxy, what does that mean for us? Are we a fluke, a cosmic inevitability, or something else entirely? JWST doesn't just look outward, it turns our gaze inward. It asks who we are, where we came from, and whether we're truly alone in the vast cathedral of stars. In the final section, we'll step beyond science and theory, into the realm of wonder. We'll explore how JWST might help us understand not only the beginning of the universe, but what, if anything, came before time itself. Can this telescope give us hints about dimensions beyond our own, about universes before this one, and ultimately about the limits of knowledge? Imagine standing at the edge of everything, the very beginning of space and time. Behind you is a vast, expanding universe teeming with stars, galaxies, black holes, and maybe even life. But ahead of you is something else. A darkness so absolute, so unfamiliar it defies comprehension. That's where the James Webb Space Telescope, JWST, is now peering. Not just into the past, but towards something far stranger. The question of what came before time itself. Let's be clear. Time, as we understand it, began with the Big Bang. According to the standard cosmological model, roughly 13.8 billion years ago, all matter, energy, space, and time emerged from a singularity, a point of infinite density and temperature. But here's the thing, singularities are where the math breaks down. The equations of general relativity go haywire, and the known laws of physics dissolve into mystery. For decades, we've treated the Big Bang as the ultimate beginning, but what if it wasn't? This is where JWST comes in, not to prove what came before the Big Bang directly, but to help us see whether our assumptions about the Big Bang are even correct. By studying the universe's earliest light, ancient photons stretched by billions of years of expansion, JWST may detect imprints or anomalies that suggest a pre-Big Bang reality. If the cosmic microwave background, the afterglow of the Big Bang, is the fossil of the universe's childhood, JWST's infrared view is giving us a peek into its infancy, and perhaps its ancestry. Some theories suggest that our universe is just one in a never-ending cycle. The cyclic model, championed by physicists like Roger Penrose, proposes that the universe goes through infinite cycles of expansion and collapse, big bangs followed by big crunches over and over again. In this view, time never truly began, it just transformed. Each aeon, as Penrose calls them, gives birth to the next. The remnants of black holes from a previous universe could be the seeds of structure in our own. Another possibility is the multiverse. Not science fiction, but a consequence of inflation theory, a brief period of exponential expansion right after the Big Bang. Some versions of this theory suggest our universe is just one bubble in a vast cosmic foam, with countless others forming, expanding and dying independently. If so, JWST might detect strange patterns or gravitational anomalies that point to other universes pressing against our own, cosmic fingerprints left by siblings in the multiverse. There's also the concept of a quantum origin to time. Quantum gravity, a still developing theory that seeks to unify general relativity with quantum mechanics, suggests that time itself may be emergent. In the earliest fractions of a second, space and time may not have existed in the forms we recognize. Instead, there could have been a pre-geometry, a timeless quantum state. If this is true, JWST's ultra-deep field surveys might not just show us galaxies, they might hint at the transition from a timeless state to the first flickers of chronological order. And yet perhaps the most mind-bending idea is this: what if time isn't linear at all? Some interpretations of string theory suggest that the universe is a hologram, that everything we experience is a projection from a deeper, more fundamental reality. In such a framework, time as we perceive it could be a byproduct of how we interpret information, not a fundamental property of the universe. In this case, JWST isn't just a telescope, it's a decoder of illusion. Now, none of these theories can be proven by a single image. But what JWST offers is data, unprecedented, high-resolution, ultra-infrared data that allow scientists to test these ideas in ways never before possible. If we detect galaxies with properties that contradict standard cosmology, or background radiation patterns that don't align with inflation, or unexpected elemental abundances that suggest a pre-Big Bang state, then the door opens wider. These aren't just questions for astrophysicists, they're questions for all of us, because to ask what came before time is to ask what we are. Are we the inevitable outcome of physical laws, a miraculous accident, a spark in a cycle stretching eternally forward and backward? JWST doesn't offer final answers, it wasn't built to, but it brings us closer to asking the right questions, and that perhaps is more powerful, because every question we answer leads to 10 more. Every mystery solved gives birth to new wonder, and in this golden mirror suspended in the cold void, we see more than galaxies. We see ourselves, our curiosity, our hunger for meaning, our need to know. So, what's next? That's up to you. If this journey stirred your imagination, if you felt the pull of the stars and the tug of something beyond, share this video with someone who needs a little more wonder in their day. Like it if you were inspired, and drop a comment. What do you think came before time? Could JWST ever reveal it? Because in the end, space isn't silent, it's speaking, and with each new image, the cosmos whispers just a little louder and waits for us to listen. Thank you for joining us on this journey through space, time, and the mind-bending frontier beyond. Until next time, stay curious and keep watching the skies.